Hi folks, today we're going to start on Krebs cycle mechanisms number 2. And we're going to try to get through alpha-ketoglutarate dehydrogenase and succinyl-CoA synthetase and our coenzyme Q using reaction in complex 2 or succinate dehydrogenase, fumarase and malate dehydrogenase. So we're going to try to finish it out with this one. And so currently we are on to enzyme 4 in the cycle, which is alpha-ketoglutarate dehydrogenase. And this enzyme uses TPP. Remember that this is a very similar enzyme to pyruvate dehydrogenase, which means it has E1, E2, and E3. And so E1 would be isocitrate dehydrogenase, or sorry, it would be alpha-ketoglutarate dehydrogenase. 2 would be lipoamide, or dihydrolipoamide. Or lipowheel, I suppose. Transacetylase. And then dihydro, lipowheel, dehydrogenase. And so remember, just like in pyruvate dehydrogenase, each of these 3 enzymes gives off a specific product, CO2 from the first one. In this case, it'll be succinyl-CoA. It was acetyl-CoA for pyruvate dehydrogenase, and then this guy is going to give us our NADH. And if you want to go back and review the pyruvate dehydrogenase video, that'll be easy to link to. We can do that down in the comments. But the idea here is, remember that we have our TPP in enzyme 1, and we are currently working with alpha-ketoglutarate. And remember what TPP does is it allows us to make or cleave alpha carbonyls, right? So in this case, we're going to be cleaving off the carboxyl group. We're going to be doing a decarboxylation at the alpha position. And remember that this is an ylid, so it has a nucleophilic pair on the carbon. So we're going to be attacking here at the carboxyl group, or the carbonyl, the alpha keto, next to the carboxyl group. And now, since our nitrogen is correctly positioned, what we can do is eliminate the CO2. So we're going to make the CO2 itself. So we're going to form the C double bond O, the double bond O, CO2. This bond, CC bond is going to break, go up onto the TPP, and give an electron pair back to the nitrogen, which is always happy to have electrons, especially if it's positive. So we will form our complex here, TPP. Recall that this is a resonance form. With a nucleophilic character at that old position. And at this point, we're going to be attacking the lipoamide. Recall when we're going to do the old transacetylase. So we'll hand this on TPP. In this case, it's not the hydroxyethyl TPP, but we will be doing the old handoff. I don't want to spend a whole lot of time going through this mechanism because you guys already should know it from pyruvate dehydrogenase. We'll attack here, grab a hydrogen, and then we'll cleave off our TPP. And then we'll have a lipoamyl, succinyl-lipoamide, I suppose you can call it. And then we'll hand that off to a CoA on the next step, and then we'll recharge the lipoamide on enzyme 3. Again, those ones are going to be literally identical to the steps in pyruvate. We're just going to cleave off the acetyl group by having a CoA come in and attack at this position. We're going to have up, down, goodbye lipoamide. Or I suppose really grab a hydrogen as a leaving group, and we will now have a succinyl-CoA. And we will at this point be handing off to our enzyme 3 to make the NADH. Okay. So we have now generated our CO2, succinyl-CoA, and NADH from enzyme 3. So if you want to go back and review that, I go through it in great detail in pyruvate dehydrogenase, same exact mechanism. Okay. But essentially at this point, now we have a high energy bond. And that high energy bond is the thioester bond. Succinyl-CoA. So at this point we are on to enzyme 5, succinyl-CoA synthetase. And of course, in order to do this, we are going to be generating our reaction. We're going to be using succinyl-CoA. We're going to be making that into succinate. So we're going to be cleaving off that CoA. But we're also going to be doing a substrate level phosphorylation. So we need a phosphate and a GDP for this. And we're going to make a GTP for this as a product. Okay. So what we're going to be doing here is we're going to be taking this thioester bond, which is a relatively high energy bond, not super high energy, but we're going to be trading it up for a high energy bond using a phosphate. Okay. Then we're going to use that acetyl phosphate to generate a GTP in a very similar way as to what we saw with phosphoglycerate kinase in glycolysis. Right? There's a lot of cool similarities here between the two. But the mechanism for this is actually very, very clever. We have a phosphate, a free phosphate. Okay. That's going to be a nucleophile. We will be attacking here in a way that was a little bit similar to phosphorylase. In glycogen, of course, that was working on reducing sugars, not on dicarboxylic acids, but keep in mind that that's a possibility. You can think of it as a inorganic phosphates doing the cleavage here. So we'll end up with a tetrahedral intermediate. And then, of course, these guys. And we're going to kick off our CoA by grabbing a hydrogen. And now we've generated an acetyl or a succinyl phosphate. And that's our key intermediate. Succinyl phosphate. That is going to now be used to shove its phosphate onto the GTP, or GDP in this case, to make. So now with this acetyl phosphate group that we see right here, compare that to 1,3-BPG in glycolysis. Remember that phosphoglycerate kinase did the exact same thing. We took this 1,3-BPG and we stuck the phosphate that was on the acetyl group onto a nucleotide. So this is a very similar reaction to that. That was phosphoglycerate kinase. This is succinyl-CoA synthetase. Again, synthetases and kinases are very similar reactions. They're both ligases. In this case, we're going to be using an ATP or GTP to attach things to each other, as opposed to just transferring a phosphate like a transferase. And so in this case, we have now a succinyl phosphate, and we need to add one more thing and get the phosphate off. So succinyl phosphate. So at this point, we have a water is going to come in and hydrolyze. So we're going to need to pull hydrogen off to make that nucleophilic. We're going to attack here. Up. Okay. And then we're going to neutralize and kick off our leaving group. The best leaving group here is going to be the phosphate because it's resonance stabilized, so we're going to kick that off. But in this case, not going to give it back to the oxygen. We're going to be using this to go onto the GDP, so attacking another phosphate. So I'm just going to draw G for guanosine. And so we have GDP here. I'm actually going to clean this up just a little bit so our arrow goes to the right spot. This is now going to attack at the beta. We're going to come up and down, and then we're going to liberate a water. So we're going to be dehydrating. But we will now have a succinate. And a GTP, and I suppose a water out of that. Now we've had waters come in and out, so I guess technically that water won't show up in the full balanced equation, but a water was given off in this step as part of GDP. Okay. So now that is the end of succinyl-CoA synthetase, and now it's time for complex 2, the succinate dehydrogenase. And in fact, this mechanism, and we're going to go in deep in the future. We're going to have complex 2. It's so important that it gets a Roman numeral name, succinate dehydrogenase. Okay. So there's two phases of this. The first one is succinate, goes to fumarate, fumarate, remember, is a trans-alkene. We are going to be making a C double bond C. There's no polarity here, and FAD is really good at doing these kinds of reactions where we generate a non-polar carbonyl, or a non-polar alkene in this case. So we're going to be really doing FAD. And you remember the shape of this guy. Vitamin B2 riboflavin. And down there. And then we're going to be making FADH2. Okay. And then the second one is going to be handing off from FADH2 in the enzyme. Remember that FADH2 is stuck on enzymes. It doesn't really float around and do anything. It's stuck to enzymes. And we're going to pass those electrons off onto coenzyme Q to form coenzyme QH2 and FAD. Okay, so the net reaction is succinate plus Q goes to QH2 plus fumarate. And so the electrons ended up on coenzyme Q. We're going to go deep into this mechanism when we get into electron transport. And so I don't want to dig that deep right now, but I will draw you the structures of some of these as we get there. So the next one we're going to run into, again, that's really all you need to know because I'm going to go deeper into it when we get to electron transport. The next one we should talk about is the next one in the chain, fumarase. So that's 7. This is just a simple hydratase where we're going to add water onto it. We're just literally attaching a water. So this is just going to be hydrating the double bond. So fumarate plus water goes to malate. So we're just adding our double bond. And this is one that we're probably going to look very familiar from organic chem. In this case, it's going to be L-malate. It always goes on the left-hand side just because of the enzyme. So we're going to pull that hydrogen, attack here, grab a hydrogen. Not much more to it than that. This is a very simple enzyme. We've now added water to our double bond. It is now specifically L-stereochemistry. And that malate now needs to be completed. Malate dehydrogenase. This is the first mechanism we ever learned in biochem in terms of redox, where we are just going to pull off a hydrogen and transfer onto NAD. So malate plus NAD goes to OAA, oxaloacetic acid, or oxaloacetate plus NADH. NAD So again, we're going to pull off a base, transfer on that hydrogen here, give a pair back to nitrogen, and then that will have given us our oxaloacetate. Don't get confused by the fact that I drew that on the right. There is no stereochemistry for a carbonyl. And so it's now a prochiral center, so it's not worth even worrying about the fact that that's right or left. You can draw it either way. And we are officially done with the mechanisms of the Krebs cycle, except for complex 2, which we need to go in depth and talk about iron sulfur clusters and relays and all the stuff that we're going to talk about for electron transport. So that's the only mechanism that you don't have, but these are very elementary mechanisms. You should know all of them for the exam, and I would certainly be comfortable asking you to push arrows for multiple mechanisms for the same thing. Okay, so keep that in mind here. All of these guys are going to be traceable. I would expect you to be able to follow a carbon all the way through 1 round or 2 rounds, which is what we're going to talk about in the next cycle, in the next video, and be able to follow a single carbon until it's lost as a CO2. So any of those carbons, I would be wanting you to trace them all the way through to CO2. So we'll do that in the next video.